I can stay. Anyway, so this was done very fast last night, so don't expect too much. Anyway, the idea is to show the spectra of different experiments. We are going from space to indirect measurements. Of course, we have different like Calette, Dampe, and others in space, and then we have LASO, Hawk, and others, and Telescope Array and Auger. Now, if you consider that the cosmic ray flux is shaped by the injection spectrum and the transport, and you assume that the cosmic ray is given by a power law, then taking the diffuse acceleration model for the injection and as such having a power law there, then you end up with a time of confinement which is the same from 20 GeV when the solar modulation stops or up to at least 10 to the 15 or so, 14 or 15. So in principle, you would expect a single power law, but this is not what it's measured. And here you see that starting with Pamela and AMS-02 to go to others, they saw, first of all, this hardening, which is at around a few hundreds of GeV, and then the softening here at 10 TeV. This is seen both in proton and helium, for example. So it's clear that already at the beginning, it was clear that the power law was not the correct thing, and there were a lot of breaks. So here we had different presentations in which, for example, for Calette, they showed the same thing, 533 GeV for the hardening, and then a softening at 9.8 TeV. And if you take the helium, again, you have exactly like in Dampe, also in Calette, you have a similar softening at 33 TeV. Of course, the breaks in helium appear at a different position compared to those of the proton if you plot them in energy per nucleon, but since the acceleration and transport depend on the Larmor radius of the particles, if you plot them in rigidity, you see that they align perfectly. Now, if you just take a very simple ratio between helium and hydrogen, I don't see why this does not change, but for some reason I see a different slide. Anyway, the break of the helium to the break of the hydrogen is of the order of 2.5, both in Calette and in Dampe. And we saw that LASO, I don't know why, what's wrong? Lost the internet. Anyway, LASO is expecting to see, it's reconnecting. Yeah. Now it's not my fault, huh? I tell you, you should trust. Yeah, exactly. So if you take, now it does not change the slide. Very slow, yes, okay. We saw that LASO is expecting to see something like you see in the plot on the right in 1 year from now, more or less, for the iron. And if you take the iron to the proton, you have around 26. So we could say that from Dampe and Calette, there is they surely favor a rigidity dependence of the spectra, and we will see if with LASO we will have a similar conclusion in some time from now. The same things have been shown for different elements like carbon and oxygen. Again, you see that This is a comparison of Calette with Dumpy. And you see that they are quite compatible. And in the bottom plot, you see the iron flux from Calette. And in all these cases, there is anyway a problem in the spectrum normalization between Calette and AMS, which should be explained. It's I don't know if it's understood up to now. It was asked during the talk, but there was no motivation for this, at least at the current stage. Of course, if you want to go up in energy, you need to go to the indirect measurements. Here you see the all-particle knee, which is consistently observed by LASO, HAWK, IceCube. You see also in this plot top right that the measurement of Dumpy is nicely connecting the indirect measurements to the more direct results. This is the result of HAWK, and this is the famous Cascade Grande measurement where you see that if you divide the heavy from light in some way, you can see the end of the heavy galactic components around 10 to the 16.8 or so, and you see the onset of the proton, extragalactic protons above 10 to the 17 electron volts. There is an interesting point here that if you look at the proton spectrum here by Cascade, by iSTOP, you see a difference here. And Lipari and Bernetto published a paper on this in which they discussed how you can connect these points to this part. And if you want to continue from the softening up to the highest energies in the same way, you end up with a slope of 2.87. But if you want to make a connection with iSTOP, you need a different thing. So you have to have a gamma that is given by a formula like this, and you end up with a quite different slope. And in grapes, we saw that there is similar structure here at around the same energy of 150 TeV. Okay, now it does not move for some reason. No, yes, this is iSTOP, the composition of iSTOP. At the highest energies, we have, as you know, two experiments. You see on the top the two energy spectra of a telescope array and Auger. The systematic uncertainty here in the lowest energy part, below 10 to the 19.5, was in the past here around 9%. It was shown by our colleagues of telescope array that if they use the same fluorescence yield that we use in Auger, which is more precise than what they used before and more recent. And also they use the same missing energy that we use that we add to the calorimetric energy to obtain the energy of the primary. This difference becomes of the order of 1 or 2%. So what we can conclude is that from this point of view, the two spectra are in very good agreement up to here. Then you see here, there is a problem. The spectrum of telescope array is different from the spectrum of Auger. And we had, for this, we made a lot of work together in a working group and studying the systematics that could have caused this. We corrected for all that we could find, and we couldn't explain this at least up to now with some other systematic uncertainty. We tried to see if there is a declination dependence of the spectrum. This is the result of Auger. In 3 different declination bands, you see that we don't have any dependence of the spectrum. The small differences that you see here above 8 10 to the 18 electron volts and above are in agreement with the level of anisotropy that we see with the dipole. So we conclude that we don't see any declination dependence. On the other hand, the declination dependence is seen by telescope array. In red, you see the declination band that is superimposing with Auger. In black, the northern part. And what was claimed by TA is that this is an astrophysical reason. The spectra are different in the north and in the south. This is something that John showed at this meeting. You see here in the left part of the plot, this is a fit. The red line is a fit to telescope array and Auger over the full aperture, where Auger data are plotted in the common declination band. And here on the right, you see what happens if you plot the points of telescope array, but subtracting what they see as excesses in the hotspot and in the excess which they call Perseus species excess. This has been obtained with different cuts on the spectrum compared to the cuts that were applied to the spectrum of telescope array that I showed before. And as I showed this morning, we have a different conclusion on this for the moment. You see that, again, as I explained, if we use both the vertical and inclined events, we can, with the inclined events, reach 45 degrees north in declination. And you see that both here and here, we cover quite a large part of the excess of telescope array and its center. And if you look at the numbers and check if what is the number of events that you expect, you see that we compensate because we are very much bigger than them. So even if the exposure is not complete like theirs there, our total exposure is much bigger. So we compensate. So at the end, we have a similar number of events expected. You see in this column an expected TA and expected Auger. They look very much similar. So we have data of similar size, and they claim they have excesses that at the moment are at the level of around 3 sigma, depending on the excess, 3.2 for the hotspot, and we don't see anything other than isotropy. And so our conclusion for the moment is that we cannot confirm what they say, that the difference in the declination is due to these excesses in the northern sky. This is, of course, a very difficult analysis for both of us, and we are still working together in a working group, planning to continue and to try to understand more. This is clear. And finally, I have a slide on the composition of Auger and telescope array. This has been a subject of a lot of discussion in the community. Many people keeping saying that Auger is a heavy composition and TA is a light composition, but you cannot, you know that in both cases we don't measure the mass, but we measure the distribution of the X max, the depth of maximal distribution of the showers. And then we use, for example, in this case, the two moments, the mean and the standard deviation. We cannot compare directly. If you take two publications of Auger and TA, you cannot just compare directly the X-max distributions, because in their case, due to the fact that they have lower statistics, the result is folded with the detector. While in our case, we can unfold and publish the result, having subtracted the effect of the detector. So what we did together in another working group that we set up, Auger and TA together, we provided to telescope array our mix composition the best fit of our composition, and they use it as an input to their calculations, and included their detector effects in there. And this is what you see here called the Auger mix. So you see that if you compare the Auger mix seen by TA, and you have the red points, to what TA alone see, you immediately see that despite the fact that we have very different systematics, within the uncertainties, everything is fine. So the conclusion in this case is that the composition from telescope array is compatible with Auger mix. Of course, it's compatible also, as they say, with the light composition, because they cannot distinguish. But on the other hand, Auger is excluding a constant composition, because in our elongation rate, we can exclude a constant evolution at 4.4 sigma. So this is the problem at the highest energy. We have, of course, you see once again that this points to having more events to look at composition in the suppression region, because we don't go above 10 to the 19.5. So
thank you, Antonella, for this. I mean, John probably wants to comment on that, but just, I mean, if I take the view of in particle physics, that if there is just 3 sigma difference, there is some tension, but I wouldn't speak of inconsistency in the strict sense, right? And now with the energy spectrum. No, I mean, just in general, if there's 3 sigma difference between two measurements,
yeah.
I mean, one needs to keep an eye on that, but one would not claim that they are consistent. I mean, there's tension for sure. Now, I mean, to the question of the energy spectra, if we look at the TA data with a bump around the hotspots, and if Auger doesn't see any, so John, that is 3 sigma, 3.2 sigma, or what do you say? The significance of the excess near the hotspots or in the hotspots? The excess of events.
The excess of events in the hotspot is about 3 sigma.
Yeah.
3.2, it's written here in the last line.
It was higher before. It's less significant now. That there's still some excess there, but certainly not as bright as it was in the first 5 or 6 years.
So that means we should not possibly, I mean, it's interesting to see, but we may not be too excited about that, that there is inconsistency, right?
Yes. Some people like to say 3 sigma and a couple of dollars, you can get a cup of coffee.
Yes.
You know, is it statistical? I don't know.
Yeah.
Is it real? There's some hints that it's maybe real.
Yeah.
But
yeah, exactly. I think it should be taken, I mean, in that way, right? And
3 sigma is something which is always dicey.
Yeah.
I remember in the early days of Auger, you had also seen some excess, right, in direction of Senex.
That Centaurus A, no, that always was there. I mean, but the Veron, SETI Veron.
VCV catalog, yes,
VCV
it was, it went, it became lower and lower with increasing statistics, yes.
Yeah.
And that was even less than 3 sigma, actually, right?
So this is a very good in picking out 3 sigmas, you know, we are very, very aware of it. I wanted to ask, since both TA and Auger are upgrading their detectors by adding more elements, so how do you see that play out in terms of, you know, measuring composition? Because now you will have more constraints, right? So is there any idea that, you know, because say compared to 5 or 10 years back, there was a lot of differences between TA and Auger. Now, thanks to this working group, I think you guys have really brought these discrepancies, or let's say disagreement, down to almost manageable level, right? It's a couple of % is not something to.
But in our case, as I said this morning, we we did the upgrade to have the 100% duty cycle of the surface detector for the composition, because otherwise we cannot go through with the fluorescence detector alone. But still, we need the fluorescence detector exactly as we discussed before. We need an independent measurement. This is another example of what Ralph was saying before. This morning I showed the composition up to 10 to the 20, more or less, when we use the surface detector parameters and the deep neural network. But if you compare what we find at the Monte Carlo level, everything is perfect. And it's not, because when you compare with an independent measurement from the FD, you see that there is a bias.
Yes.
And the bias is big.
Okay.
So it's again an example that we need an independent measurement.
Right. So do you hope that you will be able to shrink the error in Xmax measurement, or in terms of the dispersion that you see in Xmax? Will those parameters will be better constrained with this, say, radio detection and things like that?
We hope so, and we hope to go up in the suppression region.
Is yet another type of measurement there. I mean, it looks very promising, but we have to really prove, I mean, that we reach that precision. We should be, I'm always conservative. I mean, but we should not promise too much, but it looks good.
Yeah, at the moment, with the first measurement by the radio of the Xmax that was done with the engineering array, they have a resolution on the Xmax which is comparable to that of the FD. So in principle, if this is confirmed, of course, it's sort of preliminary because it was an engineering array, a small one. But if this is confirmed, this would be very good.
Just a quick question, because I'm a bit lost in this discussion. If the TA hotspot and the warm spot region were not the answer to this bump, then what would it be? It looks like there's only one
can tell us.
hypothesis.
We don't know.
Okay, there's no other hypothesis.
We don't know.
But regarding the radio, I just wanted to comment, because we go to very inclined showers, for example, here in the anisotropy comparison with telescope array. And if we have the radio antennas working, we actually can say whether that's light or heavy primaries or something else in the inclined range that we would not be doing in any other way. So that actually could really help us a lot to understand what's going on.
And if I may, and it will come back to the Murn again, the EOG, the TA energy scale is anchored to QGZ2-3 proton simulation. If you have a different evolution with energy of this model on the number of Murns, etc., that may influence the energy scale. So I think there was some investigation in TA trying to use different things, and they didn't find a, but I don't know how, if it's strictly the exclusion of this. And then there was a work also from Quentin, where you could look at the distance of 800 meters might not be optimal to actually reconstruct the energy scale, or for the energy proxy. And this may play a role also. So I don't think everything else is excluded, or there is some systematics which might be underestimated, or I think.
Yeah, Ralph, you wanted to say something?
I only wanted to say that there are many indications, but none of those studies were conclusive, also from Quentin. So we don't really know right now where the difference comes from, because the effects seem to be small. And so it's not clear.
In TA, you did some check about the optimal distance and the constant intensity cut and other things, and none of them was particularly to explain this, right?
Now we get the same answer with the constant intensity cut. Degrees also within like 2% of this. So whether you analyze the way we have always analyzed with Monte Carlo and comparing, or if you go back and you use constant intensity cut, that's no different. That's not the answer to this problem.
Yeah, so perhaps we have to be a bit more patient, wait for more data, but this one paper that you showed, Antonella and John, about the that actually that is about to be published now, right?
It's on the archive.
There is one archive paper by TA with this claim, and there is, or there will be tomorrow, another archive paper from Auger, which includes this analysis. It's a search on the excesses around the supergalactic plane. So within that search, we also checked this.
Yeah, okay.
We hope to have publications soon.
Yeah. So, Tanguy.
Yes.
Could we go back then to the muon issue and strangeness to the models?
Yeah.